Hey everyone, this is Andrew. Welcome back to the channel. In this video, I will be discussing the IUPAC Nomenclature of Alkynes, some theory about alkynes, and we're going to run through some practice problems. So without further ado, let's hop right into it. So to begin, an alkyne is a hydrocarbon that contains a carbon-to-carbon triple bond. Recall that a carbon-to-carbon triple bond results from the interaction of two sp hybridized carbon atoms. The two sp hybrid orbitals of carbon lie at an angle of 180 degrees to each other along an axis that is perpendicular to the axes of two unhybridized 2py and 2pz orbitals. When these two sp hybridized carbons approach one another, one sp to sp sigma bond and two p to p pi bonds are formed. The two remaining sp orbitals then form bonds to other atoms at an angle of 180 degrees from the carbon-to-carbon bond. The length of one carbon-to-carbon triple bond is 120 picometers. The strength is approximately 965 kilojoules per mole. This makes it the shortest and strongest known carbon-to-carbon bond. Alkyne nomenclature follows the general rules for hydrocarbons that we've discussed in previous videos. The suffix "-ine" or "yne" is used, and the position of the triple bond is indicated by giving the number of the first alkyne carbon in the chain. Numbering the main parent chain will begin at the end nearer to the triple bond so that the triple bond receives the lowest number possible. Compounds with more than one triple bond are called dienes, with three triple bonds would be trienes, and so forth. Compounds containing both double and triple bonds are called enenes, or ENYNES, if you want to spell that out. Numbering an enene chain starts from the end near the first multiple bond. It doesn't matter whether it's a double bond or a triple bond. So let's take a look at this first example. We see that we have carbon atoms 1, 2, 3, and the triple bond is equidistant from both ends. So let's just start from this side since I already numbered it 1, 2, 3, and we'll go in order. 1, 2, 3, 4, 5, 6. We got two methyl groups. We got one here and one there. And the triple bond starts at the third carbon atom. So we got 6 carbons. That's a hexane. With a triple bond, it'll be hexyne. We have two methyl groups, one on carbon 2 and one on carbon 5. So when we name this, it's going to be 2,5-dimethyl 3-hexyne. Now let's take a look at this second example. We'll start numbering the chain from this side, it's nearest the end. So we got 1, 2, 3, 4 carbon atoms in the parent chain. We got two methyl groups. We got one up here and one down here, both on carbon 3. So this is going to get the name 3,3-dimethyl. So we have 3,3-dimethyl, and the triple bond starts on the first carbon atom, so it's going to be 1-butyne. So now let's look at this third example. We're going to start numbering from this end. 1, 2, 3, 4, 5, 6, 7, 8. So we have an octyne, an octyne parent chain. And we've got two methyl groups. So how are we going to number this? How are we going to name this? So this is going to go 3,3-dimethyl, because there are two methyl groups on that third carbon atom of the parent chain. 3,3-dimethyl 4-octyne. Let's take a look at this next one. We're going to start numbering from this end. 1, 2, 3, 4, 5, 6, 7. So we have a heptyne parent chain, and we see that we have three methyl groups. The first one is on the second carbon atom, and the next two are both on the fifth carbon atom. So when we name this, it's going to go 2, 5, 5, trimethyl 3-heptyne. We got an interesting one here. So, where do we start numbering? Pause the video, then you can come back and check. We're going to start numbering from this carbon atom right there, because that is the first carbon atom that contains the triple bond and also will contain the substituent on the lowest number carbon atom. We would not go from this carbon atom and around this side, because that would give this a higher number, and we don't want that. So we're going to start here. It's going to go 1, 2, 3, 4, 5. And we'll just continue numbering so we see how big of a chain we have. But this molecule is a cyclodecane. See, we have 10. So it's dec. So this gets the name 5-isopropyl, because that's what that substituent is. It's an isopropyl group. We have a CH right here, and then we have CH3s on each end. 5-isopropyl cyclodecane. We don't put a number in front of the ine because we assume that it's on the first carbon atom because there are no other substituents. And the isopropyl we numbered as 5. Okay, so we've got an interesting one here. We see that we have double bonds and triple bonds in this compound. So which end are we going to start numbering from? We'll start from down here. 1, 2, 3, 4, 5, 6, 7, 8. So we have an octyne. And we see that we have a double bond on the second carbon atom and the fourth carbon atom. And we have the triple bond on the sixth carbon atom. So when we name this, we're going to go 2, 4, octadiene for the double bonds. And this gets weird, 6-ine to recognize the triple bond that is in the compound. 2,4-octadiene, 6-ine. This is an easy one. We have 1, 2, 3, 4 carbon atoms, and the triple bond lies on the second carbon atom. So this is 2-butyne. 2-butyne. Double bond gets priority, so we got 1, 2, 3, 4, 5 carbon atoms in the parent chain. This is going to be 1-pent-N for the double bond, 4-ine. In this one, we see we have a chlorine atom that doesn't change up anything. We still have 1, 2, 3, 4. The chlorine is on the fourth carbon, so we go 4-chloro, 1-butyne. 4 carbon atoms, we get the but, and it's on the first carbon atom. 4-chloro, 1-butyne. So this looks like an interesting one. We're going to start numbering on this carbon atom, so we got 1, 2, 3, 4, 5. And we're going to end up having a methyl group. So we have a nitro group right here on the first carbon atom. We have the triple bond on the second carbon atom. We have a methyl group on the fifth carbon atom. So this gets the name, remember, alphabeticity when we name these compounds. So we got 5-methyl, 1-nitro, 2-pentyne. So now we have a double bond and a triple bond. So we go 1, 2, 3, 4, 5. So we have 5 carbon atoms. And what do you notice? The 2 heavier substituents are on opposite sides of the molecule. So this is going to designate the molecule as E. Remember that when we name this. We got E3-penten, 1-ine. So now let's take a look at this one. What do we have here? We have a cyclopentane, which will get the name cyclopentyl because it's a substituent, because the triple bond has priority. So the name of this molecule is simply cyclopentyl ethyne, because we have 2 carbon atoms and the triple bond. So it gets the name ethyne, cyclopentyl ethyne. So let's look at this one. We have a cyclohexane ring. So this is going to get the first number, this carbon atom, because of the methyl group. And we got 2 obviously 3, 4, etc. So when we look at this and we want to name this, we see we have cis. They're on the same side, the two substituents. So we got cis 1-methyl. Then on the second carbon atom, we have 2,1 propanyl cyclohexane. It's a mouthful. So now let's number this compound. We see we got a cyclohexene ring. 1, 2, 3, 4, 5, 6. Remember, 1, so we get the double bond on the lowest carbon atom. And then the rest of the substituents will follow with lower numbers. So we got 1, 3 diene or cyclodiene, cyclohexadiene. And then we have this substituent over here, which is a propanyl group due to the triple bond. So when we name this name gets 5,2-propanyl 1,3-cyclohexadiene. So now let's take a look at this one. So we see over here we have a cyclobutyl group. And then over here we have a cyclopropyl group, a cyclopropyl. So the name of this compound is cyclobutyl cyclopropyl ethyne because we have 2 carbon atoms in between the cyclobutyl and cyclopropyl groups. So now we have this problem. We're not coming up with names, we're going to come up with a structure. Draw the structure for 1,3-butadiene. So this means we have 2 triple bonds on the first and third carbon atom of a butane parent chain. So this is going to look like this. We got a 4-carbon chain, and we're going to have 2 triple bonds on the first and third carbon atoms. So now this next question, draw the structure for Z5-hepten-1,3-diene. So when we look at this, first thing you should pick out is the hept. So we have a 7-carbon chain, and we have a double bond on that 5th carbon of the 7 carbons. And we're also going to have a triple bond on the first and third carbon atom. So let's draw out the hepten. Keep in mind the 5, because that's going to come in handy for the double bond, as well as the Z geometry. So we got 1, 2, 3, 4, 5. So on this 5th carbon atom, let's draw it like this. And we have a triple bond on both the first and third carbon atoms. So just like that. And then it says we have a double bond on the 5th carbon atom. And that's what's going to designate that Z geometry. So off of here we have hydrogen atoms. So that's what the compound's going to look like. So the last question, let's compare the carbon to hydrogen bond lengths and bond association enthalpies of an alkyne, alkene, and alkane. So when we look at the bond length, we see that we go from the sp3 hybridized single bonded carbon to hydrogen atom, and then we have the sp2 and sp. So that is the order for bond lengths for alkyne, alkene, alkane, respectively. And then right below we have the bond enthalpy order. So remember, as a rule, the more s character in the hybrid orbital of an atom, the closer the bonding electrons will be to the atom, and the shorter and stronger the bond. So thank you for watching. I hope you found that helpful and insightful. If you did, make sure to turn on notifications, like, and subscribe for more content. And with that said, I'll see you in the next video. Thank you for watching.